First of all, my colleague Chris and I would like to welcome everyone to the BAR workshop, Binary Analysis Research Workshop 2025 version. So this is again co-located with NDSS. So since 2018, the workshop BAR aims to bring people in the binary research community together to interact, to create collaboration, and also share our cutting-edge works. And here is kind of a brief history of the BAR workshop. So as you can see today, we have a new record number of submissions. In total, we have 23 submissions. One very important reason is the emerging of the AI technicals. Another reason is last year we introduced the short papers, which is like six pages. So this year we have 15 full papers and there are 8 short papers in submission. And eventually, we're only able to accept 10 papers of them, and we have an accept rate of 43%. And as you can see in the history, this year we actually, have the largest amount of papers to be presented, which is 10. So it's a very good trend, and let's keep the bar high. We would like to send our thanks to our committee members. We don't have a super large program committee, but they are people from different continents. We have experts from America, from Europe, and Asia. And thanks again for their great work. So we are able to separate our 10 papers into 2 presentation sessions. The first session is about new technicals to advance our binary analysis. And their second session is more focusing on applying binary analysis technicals to solve your real-world problems. And we're also honored to welcome 2 keynote speakers. The first one will be Professor Jack Davidson from University of Virginia, and he will talk about no source code, no problem. And our second keynote speaker will be Professor Hen Ying from University of California, Riverside. And Professor Ying will talk about writing customized transformers for binary analysis. So combining everything together, we're able to put an agenda like this. Because we don't have tons of time, so we have a pretty compact agenda. We have to start at 8:45, which is now. And after my brief introduction, we will have our first keynote from Professor Davidson, and then we will have a short break. I want everyone to pay attention to this. We don't have 30 minutes. We can only give you guys about 20 minutes for the break. And then we will have the first session in the morning, which will run from 10:20 to 12 in the noon. Then we're going to have our lunch. Following that, we're going to have our second keynote. And then after that, we're going to have our second presentation session. At the end, we will announce our best paper. We'll be able to give some small gift to their awardees, thanks to the support from Vector35, the creator of Binary Ninja. So thanks again for coming to this workshop. And here you can see the links to our homepage and also the full schedule of the program. And so that's pretty much a brief introduction from my co-chair Chris and myself. So now I would like to introduce the first keynote from Professor Jack Davidson. So the title of their keynote is No Source Code, No Problem. So Professor Davidson is going to talk about 20 years of research in binary analysis, binary writing, and resilience. Before the talk starts, I would like to give a introduction to Professor Jack Davidson. Professor Davidson is a professor of computer science at University of Virginia, and he is a fellow of ACM and a life fellow of IEEE. He has served the associate editor of ACM Transactional Programming Language and Systems, and also Transactional Architecture and Compiler Optimization. He has also served as chair of ACM's Special Interest Group on Programming Language 2005, 2007. And he's currently serves under ACM Executive Council and is the chair of ACM Digital Library Board. And so Professor Davidson has done tons of work on addressing the challenges of binary analysis over the few years. And he has also led various high impact research projects in binary analysis and cybersecurity. For instance, IARPA security taking on software uncertain provenance, and also their CGC, their CFAR projects. So let's give a warm welcome to Professor Jack Davidson. If you need USB-C.
Yeah, and then there's supposedly a way to hook up the sound. Let's see. Glasses. Oh, okay, we're good. Okay, well, thanks for that introduction. It's really great to be here. 20 years is a long time, but yeah, my original work was in compilers, but I've always been kind of what I'll call low levels, like I'm really interested in machines and, looking at binary code and, for performance reasons and various things. So this is always this kind of work, binary analysis, thinking about looking at the bits is something I've always been very interested in. First, over this amount of time, there are so many people I've worked with on all these projects. It's just been great, and that's one of the things I'll encourage you to do is look for collaborations, because that's really the the fun thing, working with great people, trying to solve hard problems. So I'm probably preaching to the choir here, but yeah, why worry about binary code? Lots of reasons. Sometimes you can't get the source, it's closed source, third-party libraries. Sometimes, of course, malware, they're not going to give you the source code. If you're trying to analyze malware, you may need to do binary analysis. It's incredible how many times I've encountered companies that want to do something to some code, maybe upgrade it or new processor, enhanced version of processor, and they've lost the source code. I did a project a long time ago with Northern Telecom, and they have these things called line cards. This is back in the days of phones and that kind of thing, and they didn't have the source code, but they needed to upgrade the line cards, and so they were interested in basically binary rewriting to do upgrade. Sometimes I'll talk about a project where for one reason or the other, they're not going to let you look at the source code, but you can manipulate the binary. So we had a project was looking at a sonar system. I'll talk a little bit about that. The other thing is, and this is why I like binary, is there's this saying, this is Tom Rupp's at Wisconsin, he used to say, what you see is not what you execute. And that's really true. The compiler may do transformations on it, and if you're looking at the source code, there's still a possibility of missing something. But look at the binary, look at the bits they're going to execute. There's a great plug for a paper. If you've never read this paper by Ken Thompson, and again, it's a great motivation for why you want to look at binaries, this reflections on trusting trust. I mean, basically, he planted a Trojan in the Unix login program so that he could log into any Unix system. And the paper talks about how that Trojan is hidden. You could do all the source code analysis you want, and you wouldn't find it. So it's a great paper that it's really a fun read. It's really short too, but it's very deep. We've had cases where people had the source code, but they can't build the exact version that's running. I mean, because build systems, different compilers, getting things, and you really, again, if you want to focus on a particular system that's running, you need to look at the binary. Sometimes software tools aren't available. I'll talk a little bit about this. We have a project where one of the things the person is interested in is an Air Force aircraft called the A-10. It's named, sometimes they call it the Warthog, kind of weird looking plane. And they'd like to fuzz it, but all the code's written in Borland C, and there's no longer a Borland C compiler, that kind of thing. The other thing is there's still a bunch of military systems are written in Ada, and so you'd like to fuzz that. So anyway, I mean, like I said, hopefully I'm preaching to the choir. There's lots of reasons why you want to be able to do binary analysis. So just, this is going to kind of guide the talk. So you kind of started doing this back in 2003. And I'll talk about that and just kind of talk about the progression. If you look at the top line, you kind of see that over time, what happened is, early on, we focused on dynamic analysis. We didn't really have the ability to do things robustly with, binary, like changing the binary statically. And then over time, as research progressed, first then it was kind of static and dynamic analysis, you do that. But then finally, I think, and I'll talk about in 2014, things shifted and we started being able to do binary analysis and do binary rewriting robustly. And that was a, kind of a big shift in things. The other thing to notice here is kind of the dollar signs went up as we went along. I think part of that's inflation, but the other thing is as you're tackling some of these systems, especially DoD kinds of projects, the dollar signs the dollars go up because you have to have a larger team to tackle some of these problems. So first I'm going to talk about dynamic binary analysis. This is something started working on, like I said, in 2003. So we called it software dynamic translation. Other people sometimes call it dynamic binary translation. And we used it early on to tackle a lot of problems in software security. There are a bunch of, at that time, a bunch of systems out there. Sorry about that. Our system was called Strata, and kind of because we thought of it as layers, Strata thing, and basically it was this virtual, essentially a virtual machine that, would dynamically fetch code. You can kind of see that idea here, would fetch code, you figure out the instructions, and then you could do that translation step. You could do whatever you wanted to do. You could introduce instrumentation, checks, or that kind of thing. So this, made things a lot easier, and basically people would use this tool and they'd customize the VM based on what their application, what they were interested in doing. Maybe they're interested in dynamic optimization. Maybe they're interested in some kind of software protection mechanism or software, security kinds of things. There were a lot of these out there at the time. Some of the other ones were Dynamo Rio. Intel had one called PIN. So there was a lot of work going on. in how to do this. There was a company called Transmeta that didn't last very long that was using it to basically take Intel code and translate it into code for this new processor they had called Caruso that was designed for low power. And the idea was they were trying to kind of capture the laptop market where power was. Fortunately, they didn't last very long. Intel kind of, is an 800-pound gorilla, kind of stomped them out of existence. But again, you kind of get the idea behind dynamic analysis. It was very useful. There's this old saying that if all you have is a hammer, you start looking for nails. And I think, everybody was doing that, this software dynamic translation paradigm. There were all kinds of people, doing different research on that. We focused on two things. One, how to make it faster. A lot of, improvements in that, and a lot of that technology, made its way into some of the, translators we use like QMU and some of the other ones. It was being used early on to help companies like, well, they don't exist anymore, but a long time ago, Digital Equipment move, from the fax to the alpha. Apple, used this kind of technology when they were transitioning to new architectures. So you could, basically, have this kind of emulation, where you translate from one instruction set, to another dynamically. So like I said, we did a lot of work. The work we were looking at was, again, this kind of software, protection. We had a couple of, projects. The first one was funded by DARPA. And again, we're going to use, I'll give you, show you one of the things that we did. But the idea was to use dynamic translation to protect, software for Helix. It was in kind of, these critical applications. The second one, the PSOUP one that you see here highlighted, was an IARPA project. IARPA is the Intelligence Advanced Research Projects Agency. They kind of stole the ARPA part from DARPA. And this one was part of what was called the STONESOUP program, which stood for Securely Taking on New Executable Software of Uncertain Provenance. Somebody worked very hard to come up with that acronym, and then it was kind of interesting. All the people that were working on it kind of then did plays on it. So ours was PSOUP. One of the other projects was called Minestrone. I'm trying to remember what the other ones, but everybody was kind of on the soup kind of thing. And these again involve static and we're starting or dynamic, and then starting to do some static analysis. But at this point, kind of the being able to change the code, we weren't quite ready yet in terms of kind of where we were with research and capabilities. So like I said, I mean, this SDT, you can do all kinds of things with code, optimize it dynamically, enforce, from a software security standpoint, you can enforce control flow policies, control use of resources. Our take on this were two things. One, to introduce kind of mechanisms to check things like accesses and that kind of thing. And then the other one that we followed for a long time was this notion of diversity, and I'll talk about that. But that was one of the big themes, is using diversity mechanisms to thwart attacks. Not necessarily repair them. Again, you'll see we weren't really, in terms of the research period, weren't really capable of doing that robustly. So this diversity angle was something people thought, okay, this is useful. And like I said, there were a lot of people that were buying into it. I mean, like I said, our first, we focused a lot on these diversity things. The other thing that we were also doing was what's called sometimes software protection. And this is where you're trying to protect software from somebody tampering with it or discovering secrets and that kind of thing. So we had all these different transformations that we were doing, on the binary, and by analyzing it, but also this dynamic kind of interpretation of the code. And the argument for diversity, and one of the most popular or actually widely used diversity techniques that's now on most modern processors is instruction layout randomization, or that's routinely done, and that actually provides some level of protection. This is the metaphor, of course, comes from nature. Is in nature, populations tend to have diversity. It makes sense in the sense that if there's a single pathogen, if everything's a monoculture, can wipe that out. It certainly gave advantage to attackers. I mean, if everybody's running Windows NT, and somebody can come up with an attack, well, of course, then you can attack, millions of machines. So one of the other ideas is this would kind of take away that asymmetric advantage, from attackers. Is if you made every machine look different, you didn't fix the vulnerability. I mean, there could still be a vulnerability there, but the attacker, to attack a whole bunch of machines, would have to adapt, their exploit for each machine. So anyway, I mean, this was a big theme, research theme, and certainly in the DoD space, they were really interested in this notion of diversity. So one of the things we did, and I always thought this was a really cool idea. I didn't come up with the key idea. Actually, somebody named Harold Thimbley, when he was looking at viruses, kind of came up with this idea. But the idea is, what if you can make every program look like it was running a different instruction set? So that would mean, again, it's diverse, because now an attacker who's trying to exploit this would actually have to adapt their exploit to that instruction set if you're trying to, do remote code execution, etc. And so there was, a lot of work on this. And one of the things that we did here, I mean, here's kind of, the idea. Of course, if you know this stuff, memory layout, et cetera, and if it's, stock operating system, particular version of the OS, you know all that, then you can, probably, and there's a vulnerability, you can probably figure out how to exploit it. So here we did kind of, again, you see this kind of static and dynamic. We used the tool Diablo. This is a link time editor rewriter from Ghent University in Belgium. And we use that to do some pre-processing of the binary to kind of align the instructions. Of course, the x86, variable instructional length, but we wanted things aligned, because what we're going to do is use encryption to essentially, kind of simulate creating different instruction sets. So we can, have a key, and then we can encrypt the code. And then what you'll see here is at runtime, I'm going to, decode it. So anyway, this is the kind of static part of this, but done at link time, where we take, the different modules and make sure things are aligned. So again, kind of lightweight analysis, to it. We didn't have to, we had to still be able to decode the instructions and that kind of thing, but this worked, pretty well. And then we would align things because we wanted to use strong encryption like AES on the code. So you can kind of see here was alignment, so we could pad things, and then that way you could fetch the right size block of code. And then it was a simple matter, we're in this dynamic translator of kind of adapting it to do the decoding before you actually, ran the code. And again, this worked pretty well. There were a few, companies that actually did use this, and it worked in practice. So that was kind of cool. It's always nice when you do this stuff, somebody actually uses it in a product or builds on it for some other purpose. The other thing I mentioned is this notion of software protection. And this is, again, trying to protect digital assets from somebody doing it. So this was companies, especially like early on in the area of, let's say, media companies that were just, had set-top boxes, CD, DVDs. They would worry about this. One of the companies we worked with was originally called Cloakware. It was up in Canada. Then they got bought by a Dutch media conglomerate called Erdeto. Finally, they changed their name back to Cloakware because Cloakware is good. But this is what they did, is they worked with banks and things. When we moved to mobile applications, hiding or, protecting our algorithms that were running on your phone where, sometimes we call this man at the end attacks. There's a conference called Checkmate that looks at this, or a workshop that looks at this kind of thing. So we also use this technique, this kind of static rewriting for this kind of, dynamic linking and, dynamic translation for this kind of thing. And again, part of our research here was two-pronged. One was how to make this translation, dynamic translation, fast. And you see, a whole bunch of papers here where that's what we were working on. So there was kind of that part, how do you do that? And some of these techniques now are in, some of the other dynamic translators that are out there to make that fast. And I think there's still some research there, going on about how do you, speed this up if you're having to do, kind of on the fly binary, dynamic binary translation. And then, there's the application of the technique to protect things. And so kind of our first thing was back in, like I said, 2002, and this was using, Strata to do this, but then we had kind of a series of papers, kind of this progression. So again, one of the things I'll say, and especially for, younger people, just, it's like, you start working on something, and, what happens is basically you can kind of keep building on it. And of course, a lot of this was done with, outside collaborators. So always fun. Am I on the time? Oh, I got plenty of time. Okay. So now here we are in 2014, and things changed. I'll talk a bit about that. And you see now we're going to shift to static analysis. And the change was DARPA started doing these competitions. They're called incentivized competitions, where there's prize money that you can get if you solve the thing. And they've done a set of these before. The one that I'll talk about is the 2014 Cyber Grant Challenge, because I think again, and the idea behind these, you'll see, are if you incentivize people, there's big prize money. People really work hard and try to tackle a problem because people want to win that money. One of the jokes I sometimes tell people is, I went to Las Vegas and I won $1 million. And it's pretty good at, when I'm at a cocktail party, because, normally if I start talking about the stuff that I do, people start kind of moving away, from you. But then when you tell them, I won $1 million in Las Vegas, of course they think you won gambling, but that's okay. So the first one was this autonomous vehicle challenge they did. And the challenge was to drive fully autonomous, drive 142 miles through the desert from Barstow, California to Primm, Nevada. And it was through the desert, no traffic. I mean, no, other cars and that kind of thing. I don't remember how much money they were offering for this, but, there were a lot of people. I think there were 14 cars competing. The furthest any car got was 4 miles. And here's what happened to the cars. My point here is that now think of where we are. This competition got people excited about this, and yeah, they failed miserably, really, right? I mean, one of the cars, I don't know which, there's a picture of it. I mean, crashed, caught fire, burned, this one I know was made by Raytheon, was one of the competitors. I mean, crazy. But they kept doing it. You can kind of see that they did a 2005 one. I think there might, and then there was a 2007 one where they were getting better. The 2007 one it's called the Urban Challenge because they were doing it in kind of the city. So there was traffic and that kind of thing. They actually spent a lot of money hiring Hollywood stunt drivers to drive cars and, drive in the way of the thing to see, whether the autonomous vehicle. But like I said, the point is really incentivized and got people interested in, improving the thing. The Cyber Grand Challenge, I think, did the same thing for binary analysis. And I'll talk about, that challenge. But like I said, there have been other ones as well. So that was like that 2014 when they announced this. It got a lot of people excited and interested because there was prize money that you could win, and so that was exciting. So DARPA called these systems cyber reasoning systems. If you're familiar with the competition, it was couched as a capture the flag, machines playing capture the flag against each other. And there were 3 components to the game that you had to do similar to capture the flag. You had to try to find vulnerabilities that then you would exploit, right? Capture the flag on the other ones. But of course you wanted to protect your own system, so you needed to mitigate them. So this is model that. And I think this was like a really brilliant idea to kind of model this competition that way. Because what better way to evaluate the defenses to have the other teams, you're incentivized to, really figure out, can I attack, this other one? Can I still, exploit them? Can I come up with, it was called a proof of vulnerability, very similar to proof of concept for CVEs. And so this really, and I'll show you kind of the scoring, but it really forced people to really think hard about binary analysis and binary rewriting, and you'll see why. So like I said, I think 2014 was this big shift that people kind of got really more excited about this kind of binary analysis area, and we're going to really tackle some of the hard problems. So here's the scoring, how the scoring worked. There were 3 things: availability, security, and evaluation. I'll show you what there was. This was what would happen in the game is the competitors would all get, it was called a challenge bundle, and sometimes it was a single binary, but sometimes it was actually a set of binaries that kind of talk to each other in some way. Think, like, a server or something like that, a client and a server. And so, and then, you had to basically protect it. That's the, security. You had to come up, with a proof of vulnerabilities or attacks against the other things you want to do. And then, but you had this constraint of availability. You couldn't, make the code too big or make it run too slow. If you did that, you would, get 0 points. That would be bad. So for every round of the game, let's see this in a second, which, lasted a certain number of time, there would be a certain number of challenge binaries in play. And then at the end of the round, you would, get a score, and it could range in this, 0 to 400, range. So here's availability, and there were 2 parts to this. There was file size, and then, runtime. So if you made the binary too fat in what you were trying to do in protection, you would, this kind of curve here, you would, lose points. You kind of had this 20% allowance. There was no penalty. But then if you started doing that, at some point you'd lose, and then, for memory, runtime memory size, there was just a 5% allowance. For functionality, they had tests of functionality, and they looked at how many of the tests succeeded. And so, if 100% of them, you would get 1, for that. But if, you broke the code totally, you get 0. And so how many of the tests ran. So they were DARPA, when they created these challenge binaries. One, they, had seeded vulnerabilities in them, but they also, had, tests of each one. So this meant this, performance thing, the size and that kind of thing, meant you really couldn't do, kind of the dynamic runtime kinds of things. I mean, it would, you wouldn't have a high enough score. So pushed everybody into this binary, how are we going to rewrite these binaries? Kind of these binaries we've never seen. They're just handed to you in the game, and you have to analyze it, find vulnerabilities, fix them, and not, affect these 2 parameters. It was very challenging. Here's the security side of it. If any competitors throws successfully, it's a 1. If no competitor throws 1 against you, you get a 2. So there is 1 or 2. But if anybody POV'd you, you only got a 1. But if you fully protected it against everybody, the other competitors, you got 2. And then this proof of vulnerability, you had to convince DARPA, the game referee, that you had the ability to carry out a POV, and there were kind of the two things that you needed to do. You could do either one of these, but you could say, oh, I can subvert control flow. So you could basically, you had to be able to control the program counter to a certain number of bits, or if you leaked information. So there were there's 2 different types things, and so you would come up with your proof of vulnerability. You would submit it to the game engine, the referee, and then they would throw your POVs against all the different competitors and do your score. So again, it's challenging. You've got to come up with find the POV, but then come up with find the vulnerability, but then come up with the attack. Here are the game parameters, just to get a sense of it. Is they had like 40 rounds. Okay, so what would happen is at start they would introduce some challenge binaries, and then they would be in play for like 5 minutes. And again, everything, it was fully autonomous. You'll see this in the I'll show a little video clip. And typically a binary might be in probably for 10 rounds, but there was always also a passive network tab where you could look at network traffic. I don't think anybody really used that. Everybody was focused on kind of the analysis, but you could decide that you wanted to deploy a firewall rule, block something, but you had to be really careful. If you ended up blocking too much, again, you're gonna you get hit on the functionality kind of thing. This is our architecture, and what I wanted you to see here is 2 things. This notion, fuzzing, and it was really interesting that there were 7 competitors, and we all basically at some point hit on, okay, the way you find vulnerabilities is fuzzing. And at that time, fuzzing really wasn't that widely known. And so, again, it was kind of interesting that kind of all the teams kind of hit that. And you kind of see here that we had this notion of fuzzing pods. This is actually before Google started doing, their massive fuzzing and that kind of thing. So we were kind of, at least, and I think the other teams as well, were doing something similar. We had what we call fuzzing pods, and we'd fire up a bunch of different fuzzers, and we had a version, of AFL. And so you see these other pieces that relate to the game about finding a proof of vulnerability and that kind of thing. Down here, you see, this is where a lot of the binary analysis came in, where we were doing, static analysis of the binary. And one other thing, and then we had this binary rewriter that I'll come back to, because this was actually, for us, one of the key innovations. And then, of course, you could, apply patches and that kind of thing, to it. One of the things that we were able to do in order to meet that availability requirement, this is where my compiler background, came in. Or, like I said, used to do code optimization and things like that. One of the things we did is we actually re-optimized the program. So we had an optimizer, a binary optimizer, that optimized the program. And what this did is it gave us headroom to add our protections or make our changes. Because remember, if you made the binary too big, too fat, you got penalized. So we would optimize it, get rid of code that wasn't needed, and then that gave us more room. And we were again able to do that with our binary rewriting technology, which I'll talk a little bit about here. This is this binary rewriting framework we came up with that we've been using in some of the other earlier ones. We're just starting this. You see a lot of these transformations at the top are what we call diversity ones, where we're like shuffling the stack, shuffling levels, so that kind of diversity and that kind of thing. But our binary rewriting technology, what we did is we would take an input binary, and then we, so what was it Steve Jobs said, great artists, or artists, great artists, steal or whatever. We were like, okay, what we're going to do is we'll use any reverse engineering tool that can give us information. So, IDA Pro, other ones that were out there at that time, and we would take those to get information, and we created what we called an intermediate representation database. So it was kind of this synthesis of all the information we knew about the binary, and had figured out. We had our own tools as well, but it was like, and sometimes, of course, they would conflict, and then we'd have to have some resolution process to decide, which one of these things, was correct in terms of, is this a target of a branch or not, and that kind of thing. And we create, and then based on that intermediate representation, we could apply what we called our layout engines. Now, for the Cyber Grand Challenge, we had to do static, and so we had this tool called Zipper that I'll talk about. But that was kind of what, sometimes for programs, my group, we talk about what's our secret sauce, what's our competitive advantage. And this was our, big secret sauce, is that we finally figured out how to robustly rewrite binaries. Because again, if you didn't do it right and you broke the binary, you would get, a terrible score. This technology, again, I'll talk more about it, is we're using it for a whole bunch of different stuff. It's over time, it's got better and better. I mean, it was very, good here. And one of the things we could do is we could rewrite it and run our own kind of tests. You couldn't do it, extensively, because remember, it's time bounded. You've got to get something out there quickly, especially if you want to protect it before some other team POVs you and you lose points. Since then we've applied this technology to a whole bunch of different projects and that kind of thing, some of which I'll talk about here. But this was kind of one of the key things. yeah, I'm sure everybody's here familiar with all these challenges, you know, just discovering, you know, which stuff is code, which is data, function identification, you know, the control flow graph, call graph, stack frame layout, all these things you've got to figure out in order to be able to rewrite. And so we want to, you know, do the rewriting and allow arbitrary transforms without undue performance overhead, and of course not break the code functionality. So that was key. So this is kind of the key idea, and it's actually, you know, quite simple as we, you know, we do that analysis, everything, and if we want to do some kind of rewriting, there's certain instructions, and those are in red here, that our analysis is unsure about whether they're targets or not. You know, we may have an indirect branch. And so those are what we call pinned. We pin those and we tell you we're not gonna move those when we rewrite. And this is, we called it the pin and win strategy. And so, thanks. And then, you know, if you wanted to do something, you could basically do that, but you had to preserve, this should, instruction 4 should be red too, preserve those pins. And then and there's a bunch of things about how you handle, you know, branch chains, and what if you want to put something in and there's no code between pins, and locality, and, you know, things that you have to deal with. But, you know, that's kind of the key idea. We actually, has anybody ever, how many people have done a patent here? Yeah. So, you know, I'd done, you know, a bunch of patents before. It's a pain. I mean, my university, you know, likes it because they like, you know, I'm in an engineering school, so, you know, it's like some of the other, you know, people, and we actually get bonus points, you know, for patents. They're kind of worthless, really, but it's like, okay, you know, this is, you know, and be measured. And so we'd done other patents, and it had been a pain. You know, you'd submit the patent, you know, to the examiner. You wouldn't hear for a long time, and then they would come back. And I think, you know, it was kind of like, they always try to find ways, you know, to reject it, you know, thing that was just part of, I think they were given quotas or something, you know. And, you know, it would, you know, you go around and around with these guys, and you'd have a meeting with the examiner, and you try to tell them, you know, why this was, you know, not the same as that, and all this kind of. This patent went through the first time, and it was amazing. I mean, it was just like, you know, we were like totally surprised. Still, I mean, you know, it was, you know, nice from the, you know, university standpoint. I mean, but in terms of anything else, I'm not sure it really matters. But that was kind of, you know, surprising. But, you know, there's some papers out there you can look at that talks about, you know, how we do this. There's, you know, the projects on GitHub. You know, there are a lot of, you know, not a lot, but, you know, we have a fair number of people that are using it as well. And so, you know, like I said, that was nice. You know, one of the things that we're happy about, and I'll just talk about this paper for a second, is this was an evaluation done by a separate group of people. Like Eric was at Grammatech, and this was done as part of an ONR project where they did this comparative evaluation of binary rewriters. So, you know, these tools are here. Some of you may recognize some of them. What they did is they created, I mean, they got a whole bunch of applications, I don't know, like, you know, like 1,000, and they compiled them, you know, different ways, and then there were, you know, kind of these, you know, one, the null AXE, it was, you're supposed to rewrite it but not really do anything, and then the other one you're supposed to, like, you know, elate a function. And what you see here is the percentage of those test programs that they created that the rewriter succeeded on. So we were, you know, really happy, you know, that again, I think we were able to transform successfully all those, you know, binaries. Some of them, you know, are pretty terrible, you know, but anyway, so this was, I think, you know, we were really happy with these results. So let me see if this will work.
These machines behind me were built atop deck.
Oop.
engineered over 2 one-year stages of competition, and built by pioneers.
Pioneer.
Program analysis scientists, hackers, and engineers. So tonight, these machines will play capture the flag against each other. Tomorrow, we hope the lessons learned will change the field of computer security. Thank you.
There's an enormous amount of computational power ready to be unleashed here at CGC. Beneath the stage are huge amounts of electricity and water needed to power and cool the supercomputers on the stage. 300 kilowatts of power. That's enough to power 1.5 city blocks. 180 tons of water flow through these pipes at a rate of 200 gallons per minute to keep the computers on the racks liquid cooled at all times. The entire stage is air-gapped to protect the data and the systems. The air gap also validates that there's no other outside influence and no human interaction. Everything that happens inside the air gap is autonomous. Data flows through the air gap through an air gap robot that literally reads Blu-rays of burn data from inside the game. The air gap robot physically moves the Blu-ray across and outside the air gap, then drops it into a reader that goes into our scorers and visualization.
Ready? Ready. Game started at 09.
So one of the things you see here, by the way, and this was, I think, really clever on DARPA's part, they couch this as kind of like a sports event. So you see these guys are wearing referee things, and then you'll see kind of some of the commentary. So, you know, if you ever watch sports, they always have kind of the subject matter experts, right? The former, you know, quarterback or basketball player, but then they have kind of the, you know, other person that's, you know, kind of interpreting somewhat that, you know, what they're saying. And you know, like if you ever watch, sometimes, you know, they have the person, you know, down on the field and they go talk to somebody. So it was very much modeled on that, which actually I think worked pretty well. My family watched it, and they actually, you know, streamed this live, and they were going, oh, that was actually not terribly, it was not as boring as we thought it would be, you know, kind of thing. So I thought that was clever.
145 seconds Pacific.
Today, we saw machines patch many of the vulnerabilities that were activated in their software within minutes without damaging software or availability. Challenges work not because of the many who cannot imagine, but because of the few willing to make the attempt. Thank you all for your courage.
Courage. Got a lot hacked up. So that was Mike Porter, and yeah, he was. I think he did a great job, and he was. So you probably know. Sorry, I don't want to do that. You need to go to the next slide. There's a new one going on right now, and I'll talk a little bit about that. You know, but like I said, this really, in my mind, accelerated this work and excitement about binary analysis. You know, all these different things had to be done, and you know, a lot of the teams really made a lot of advances in the area. And again, let's see. Actually, yeah. So I skipped over this. I wanted to talk about this. So here's the scoring. So a team called Mayhem, which was a team out of Carnegie Mellon, although, you know, David Brumley, they spun out a company called For All Secure. Won. We came in second. So that's our. So yeah, I went to Las Vegas and won $1 million. Another interesting story is what happened to that $1 million. You know, because you know we were a university team, so you know, buy me a beer and I'll tell you about that. Yeah, you look at the score here. Notice, keep hitting that. You know, we were number 1 on security, number 2 on availability, number 4. And so this is where I kind of kick myself a bit, and where I think, you know, Mayhem, the team there, 2 things is thought about it harder and also kind of lucked out a little bit. Turned out that availability, you can kind of see here, was the key thing, is don't affect availability. So it turns out that, especially towards the end of the game, that the POV, and this makes sense, right, from DARPA's perspective, the vulnerabilities, finding the vulnerabilities were harder. And that meant they were harder to exploit. So it turns out you were better off not doing anything. And we were very proactive, like, you know, because we felt good about our technology. We could actually protect it and rewrite it, and you know, you took a penalty just for redeploying a binary, which makes sense because you have to kind of take it down and replace it with something. So there was a penalty there, and we took those penalties. At some point in the game, this is where the part is, like when I say lucked out, but I think they had a better strategy too. They, you know, talked about that, but at some point in the game, and I don't remember, you know, what point, it was kind of almost a little bit past halfway through, their system hung. And there was a meeting. DARPA, Mike Walker got everybody together and said, and asked the teams, you know, and said, okay, their system is hung. Are you okay if they restart? And he told everybody, it has to be unanimous. All 6 teams have to say okay. And it wasn't unanimous. And that turned out to be good because their system was, which meant they weren't, you know, replacing, you know, binaries and doing anything, so their availability was high. It was kind of weird. At some point, their system started working again, very near the end of the game. But at that point, you know, whatever. Anyway, so very, very interesting, you know, in terms of, you know, how the scoring worked. You know, like I said, I kind of kicked myself. We should have done kind of what I'll call simulations of the scoring kind of thing to understand things, you know, a little bit better, and then maybe realize that you know, and also this notion that, yeah, at the end of the game, the vulnerabilities are going to be much harder, you know, for anybody to, you know, POV. But anyway, it is what it is. I was happy to walk away with $1 million. And like I said, it's really, I think, got people excited, and a whole lot of advances and, you know, things after that, and a whole lot of, you know, other programs, you know, spun out of this. And so, you know, and then we, you know, a whole bunch of different papers about this. So let me look here. Okay, I think we're okay. Need to leave a little time. So again, after this, we continued to, you know, work, and one of the other programs, and this is kind of, you know, I call cool, I always like this, is we wrote this paper back in 2008 about, you know, remember we were working on diversity, security through redundant data diversity, and got it out there, and then, you know, whatever. At some point, I guess somebody at DARPA read the paper and went, wow, this is really cool. We should start a program up about it. And so there actually, this cyber fault-tolerant attack recovery was a DARPA program, you know, based on this idea of this kind of, you know, invariant diversity. And so here's the idea. Again, you know, when we're talking about diversity, it's probabilistic, you know, when we're talking about like shuffling code and that kind of thing. But here was an idea where you could actually, again, do a proof that you protected against a particular vulnerability. And the basic idea is you would create 2 variants, and we call this thing the polygrapher. So inputs would come in, and you would send it these 2 variants, and then you would monitor the thing. Now, the key idea was the 2 variants we would produce in such a way that a particular attack could only work on one of the variants. And we could, you know, kind of prove that. So here's a simple example. Some attacks require knowing an absolute address where something is in memory. So what we would do, our diversity technique, is we'd split the address spaces. So one variant, that address would be valid, and the other one, it wouldn't be. So if an attacker, you know, tried to do that, it would be detected by the monitor. And then the other part of this which turned out to be the really hard part, detecting it, but then recovering. Remember the cyber fault-tolerant attack recovering turned out to be the hard part about this program. But we were able to, do this anyway. So, it was like, oh, this is exciting. And, when we saw the BAA, we were like, gee, okay, this is our idea. Let's write a proposal. So again, we call it secret because you can know what we've done and it doesn't matter. And so you don't need to do, high entropy randomization and that kind of thing. And so we did all these different, transforms, again, using zipper, rewriting the binary, and you're going to see these there where, again, we would do things with the heap, so there were kind of separate, distinct address space and that kind of thing. Like I said, that was, pretty successful. One of the things that we were able to do, I mentioned that Lockheed thing. So that was a sonar system where the code was secret, and we were able to give our tools to Lockheed, and they could actually apply it against the sonar system, and it actually worked. So we were really the only team to be able to do that. The other thing that we were able to do is at one point DARPA said, oh, we got this ADA code that we want you to do, and all the other performers were doing source code like C and that kind of thing, and all of a sudden they're like, how do you do ADA? We didn't have any problem. Just compile the code and give it to us. We don't care, what it's, we're kind of source agnostic in terms of whatever it is. As long as you give us the binary, we do it. So that was kind of neat. So last one, this is kind of interesting because I just want to hit on this quickly. This is a project we had. This was more, I was doing network security, the kind of thing. The idea was to be able to find APTs by looking at network data, and it was kind of federated data that we were collecting network data off multiple systems. But one of the things we needed to do is do a demo, and so we wanted to run essentially kind of like a cyber range and have malware that did. So one of the things we did is we would take malware, real malware, and we were running it within our own network because we wanted all that background traffic, make it realistic, because we were trying to look for APTs, kind of, the needle in the haystack kind of thing. But of course, you got to be careful about running real malware in your network. So one of the things we did is we used our analysis tools to take real malware, and I called it defanging it. So it behaved like malware, but we knew we had defanged it so it couldn't spread outside the network. And this was actually one of the kind of key things that made the kind of what we were doing realistic, is to have this. I mean, we collected over time, we had something like 743 terabytes of network data with attacks going on in them, and so this has become a very useful data set. But it was that binary rewriting that enabled us to take real malware and do this kind of attack recreation. So last thing, this is the project, just signed the contract February 12th, and this is with a group called TRMC at DoD. So TRMC is the Test Resource Management Center, and this is actually joint with Stefan and a guy at Virginia Tech, Matthew Hicks, at looking at, you kind of see here, source agnostic techniques for code coverage crash. So this is, again, binary only fuzzing to find vulnerabilities in code. TRMC is the entity within the DoD that tests everything the DoD makes. And of course, that includes software. So this is kind of cool. We actually get to fuzz things like F-18s. That's what's going on here, is this guy is fuzzing an F-18, which I'm kind of excited about. It's like, oh, that's cool. So anyway, quickly, lessons learned. How are we doing? Oh, I think we're okay. So my advisor a long time ago, told me when I was doing my dissertation, and I was doing things like retargeting and everything. He says you got to do at least three of everything to know that you've like kind of got something generalized. And I think that was true here. I mean, when we were doing these things, we'd start out and we'd do something, it was good, but it took us like 3 times to get things right before you get it right. And that's okay as long as, each time, it's something new that you've done, but you're getting there. And like I said, this thing about if you create a hammer, look for nails, that's what we did, is we had these tools, and then it was like we went around and looked for applications of the tools. We write papers about the tools, but it's really, and if you see those grants, it was the interesting part was now how do you use it to solve real problems? And I encourage everybody to kind of, think about that as when you build something, okay, so now how can I use this, for real? In the DoD world, I mean, they call this transition. So they really, every program now has this part where if you want to keep going, you've got to try to transition it to some active, program. And like I said, okay, publishing papers is important and that kind of thing, but for real impact, and also papers too, but is to actually use it to solve some real, programs. So, look widely. If you have something, look out there for, applications. Like I said, this PCOR thing was all about, federated learning and finding APTs and that kind of thing. But actually, the thing that DARPA really liked was the fact that we created this really nice data set that included realistic attacks. I mean, in the machine learning world and cybersecurity, one of the hard problems is coming up with data sets. Companies have them. Palo Alto Networks, one of our sponsors here. I mean, I know Billy Hewlett, chief scientist, grandson of William Hewlett, founder. They have data sets out the wazoo, but they're not going to give it to you because it's customer Microsoft. One of my former students is the CTO, and talked to Kevin, and look, they're not going to give out that data. They can't. So coming up, in this case was, and seek collaborations. It's really much more fun, if you're doing things and working with people. So just quickly, future directions. Well, look, everybody's all hot about LLMs. There's paper out there, and it's certainly going to affect this. I mean, it's kind of amazing. I'm sure some of you have ever just thrown a binary at OpenAI or whatever. It, will tell you interesting things. A still open problem is this proving functional equivalence, especially at the binary level. That's really hard. We tried to do it in CFAR and made some progress, but look, I mean, if you're doing this stuff and it's what I'll call a critical system, an aircraft where a pilot's life is on the line, kind of waving your hands and saying, yeah, we think this is all okay. I mean, it just isn't going to work. So in some areas, and I think this is an area that's still, out there can we finally do decompilation? There was a whole bunch of early work. Some of my friends, Christina Cifuentes, worked on it. They had this thing called Walkabout. She was Australian, about lifting code back up to source code. I think, are we there yet? I'm not sure. Malware is certainly, an interesting area, especially, sometimes it's called armored or whatever. It's obfuscated. Can you break through that? There's work that we've done with folks about similarity analysis, trying to figure out if 2 pieces of malware are related and authorship. There's work there that's interesting. And then, of course, this whole fuzzing thing, I think there's still a lot of stuff. I mean, crash triage is still hard, figuring you can crash something, but what was it? Why was it a vulnerability, and coming up with the POV? If you want to do a report a CVE, you've got to have that. There's a great paper that was done by a class where you can go read about their work. And it's got a story about they found this vulnerability in the kernel, and that was not that hard. But then doing the crash triage, figuring out the root cause of the vulnerability, because you need to do that to report a CVE, that was the hard part. So I think there's interesting work there. All right. Well, 3 minutes, not a whole lot of time for questions, but anyway, so I was, this is a long time ago, I was reading to my kid in bed. She was little, and it was a coloring book. We were looking at this, and I read this. This was actually in a coloring book. I was like, whoa, computer science. Think about that. Does anybody know the name of that rabbit, though? That's not Bugs Bunny, by the way. All right, well, questions. Happy to take a few, a little bit. We have a couple minutes. Oh, come on. If you were in my class, I'd say I'm going to give you a bonus point if you ask a question.
So let's think.
What is the name of the bunny?
Oh, you gotta, that's what Google's for. See if you can figure it out.
Lola.
Huh? What?
Is it Lola?
No, not Lola. And some people want to say Babs, and it's not Babs either. Babs Bunny, that would be, but there is a Lola, but this is not Lola. There is a Lola Bunny, but this is not Lola. Anyway, come on, you got to have some questions. No? Oh, okay, Sebastian's going to be my friend.
Yeah, you promised us to talk a bit about the next kind of CGC challenge.
Yes.
Could you tell us a bit about it?
Oh, yeah. Thanks for adding that, because I said, so you're probably aware there's something called the AIXCC, the AI Cyber Challenge. We were actually one of the teams selected for the first round. We didn't make it into the round of 7. I mean, the theme of it is it's not binaries, it's source code. And they're really focused on using LLMs to, again, find vulnerabilities and then patch the source code, so program repair. And they're looking at different languages, Java and C and that kind of thing. I hate to say it, it was kind of a mess, and a lot of the competitors notice this is, it's not as well organized as the Cyber Grand Challenge. They kept changing the rules. In fact, first they announced the program, and then then they postponed it, and then finally they did it, and then they along the way they would change things. So it's been a little bit of a mess, but I think in the end, hopefully it will turn out. But yeah, it's modeled on the same kind of thing, and for that preliminary round, again, it worked. They would basically have these problems, like, oh, the kernel. Let's see, what were some of the other programs? SQLite. They had a whole bunch of, but it was more source code, and you had to do a patch. And part of the patch, there was it had to be a, what's the right word here? A patch a human would have made. It couldn't be something and it really needed to be a patch. It couldn't be, oh, you're protecting against, the vulnerability. It had to be, so there was going to be judgment of some human. Was this a human quality, patch? But again, how they do the final round, I'm not sure. Everything, is, the other thing is the way it works is, you submit Docker images to their, system for evaluation and, get feedback. Some of the same teams made it in. I don't know all the teams, but one of the teams that didn't make it into the Cyber Grand Challenge, but it's in this one, is TrailBits. So some of you may know them, and they have some really great tools. So they actually spent a lot of time, got into that. The Shellfish guys are in. There's a team from Georgia Tech. And then it's interesting, there's always one of these teams. For the Cyber Grand Challenge, one of my favorite teams was these 2 people from University of Utah. And it was a faculty member and his grad student. and they made it in, which, I was amazed. Similar thing, there's 2 guys that I think used to be at 4All Secure, and they, actually, I think they were one of the top teams are in it. I'm trying to remember who are the other teams. But yeah, it's going to be interesting to see. Like I said, it was not as well organized. I mean, the program manager that announced it, Perry Adams, announced it, and then it got, like I said, then it got delayed. And now she's not the program manager anymore. It's being handled by this guy that works for ARPA H. So ARPA H is the ARPA Health, which is, I'm worried about it because that's all under NIH. And if you know what's going on in the US, funding and all that kind of stuff, NIH, who knows whether they'll even, be able to continue. I don't know. So that's kind of what I, know about it. We, I mean, again, this is hindsight, kind of made a mistake in that we tried to use some heavyweight software that the company we were working with built, and it was just, and they wanted to use their software development processes, and it was just too burdensome for this kind of thing. This kind of project, you've really got to do things quickly. You don't do code reviews and have people looking at things and things. It just slowed everything down too much. But that's the way it is. Yeah. Okay.
Go ahead.
It's not so much a question, but I just want to follow up the challenge idea. So I think I totally agree that AXCC is not very organized. Hope there's nobody.
Yeah.
So I was thinking, I participated in the CGC. I think it's very well organized. So I was just thinking, you mentioned the binary similarity. You mentioned the what was that? The functionality equivalence. I just thought it was a great idea to come up with a challenge just for that. I mean, there was a program before from IARPA called Source Code, but it got canceled.
Yeah. So
I just thought it could be a great idea to come up with a challenge like that. There are tons of works, papers have been published. Why don't we just build a system and figure out who is the best?
Yeah.
That was a good idea.
Yeah. Well, like I said, I think it gets people excited, especially if there's money to be won, and you can take it and put it in your pocket. I mean, that was one of my big contributions in my CGC group. I made sure that the money didn't go to the university. It actually, our team got pretty handsome checks money. It took a lot of work to do that. I have these emails from one of the University of Virginia lawyers saying, we can't let these people put that money in their pockets. This is the university's money. They're being paid by the university, kind of thing. But I actually was able to win. There was a guy at Florida that won one of these things, and the University of Florida grabbed the money. He sued them because he claimed that he had agreement with them, and actually they ended up giving the money to the team. But some of the other teams I know, I don't know what happened. I should talk to the Shellfish guys. Were they able to, get the money, or were they? Yeah, good. I'm glad. I mean, everybody works so hard, and then you're working night and day for these competitions. That's the cool thing about them. It really gets people. You got people just, that's what they're doing, and then to go, oh well, university, thank you very much. We'll, pocket the money. Just didn't seem fair. The guy at Idaho, Jim Alice Foss, they took the money, and he was really pissed. Can't blame him. I mean, they took the money they won. Anyway, well.
To be accurate, actually, you should use the money for the hiking team.
Yeah.
So we used to pay for travel,
Oh, that's it. Yeah. So yeah, there's. Well, I mean, you could do it that way. I mean, so yeah, if the university put it in a pot that he has access to, that's okay. But I like it when it's in my pocket, you know, and I get to spend it, you know, what I spend it on, not, you know, through the university. But I do know that's the other model is, okay, you get it, but it's in some discretionary fund at the university, and yeah, you can use it to travel to conferences and, you know, that kind of thing. It's like, I want it. All right, thanks.